All right, we're good. Hi, Virg.
Hi, Mark. Hi, everybody. Welcome to our 19th episode of AP Calculus AB Live.
I am Mark Corelli from Ryan High School in Denton, Texas.
And I'm Virg Cornelius from Lafayette High School in Oxford, Mississippi. And it's been so long since I've been able to get my hair cut that I had to bust out a barrette from 1978. This is ridiculous.
Fortunately, mine's short enough. Normally, I haven't gotten to those. I did look at the clippers last night.
You looked at the clippers.
I may show up very short hair. Here's a schedule for the remainders of the weeks. You don't have to take a screenshot or come back later and pause it, or hold your camera up to that QR code. Where are we? We are right around Monday, April 20th. We're about halfway through this. And so if you want to know what we did in past, that's what we've done in the past. We are aiming for this May 12th, 2 Eastern, 1 Central for me. The actual exam, the late exams after that. It is 45-ish minutes, a 25-minute FRQ and a 15-minute FRQ, and hopefully we will prepare you for that as best as we can.
And is this picture new, Mark, or did we have this picture before?
No, this is a new one.
Oh, okay.
This was we are starting the counter again, one whole day. And that is a very windswept picture of both of us. That is at the end of the reading last year, I believe, maybe the year before, but
in Kansas City. You can see those black, we have our lanyards on still from the convention center.
We can identify the restaurant. If that's the sushi place, it's 2 years ago. If it's that's it.
We look very relaxed though, because we're obviously done with our presentations and stuff like that. So
all right. So we're going to do our warm-up in a minute. It is going to roll right into our Unit 5 review, which is analytical applications of the derivative. And then we'll let you know what's in that Dropbox. It got populated about a half hour ago if you want to go get those items and you haven't yet. So.
And I want to say too, this is Unit 5 review, and we are reviewing all of the units, but Unit 5 is really, really long, and this is just some highlights of some ideas that we're reviewing for you. Some things to make you think and go back to your notes, go back to some of your assignments, quizzes, whatever of your own. This is not like the definitive Unit 5 review forever and ever.
Right. And also some of Unit 5 is going to carry into Unit 6, and we're going to carry some of Unit 6 into Unit 7 because we have a whole week of Unit 7 videos already online. So.
Yeah. And also like math is completely intertwined. So we're reviewing everything all simultaneously.
All right. So here's our warm-up. You have a graph, and it says the graph of a differentiable function g is shown above on the interval from -4 to 4, endpoints inclusive. How many values of x in the open interval from -4 to 4 satisfy the conclusion of the mean value theorem for g of x on the closed interval -4 to 4? And Virg, do we want to show them the definition of mean value theorem first, or do you want to go ahead and do some time with a joke while they think about it?
Last week I said that I was kind of running out of jokes, and I asked people to email me more jokes, and guess what?
You got
nobody emailed me. So here's the thing. Maybe I already used up all the math jokes that there are, or maybe that's a sign that people think that the math jokes are terrible, or maybe people are busy doing other things. So I just want to do something different today instead, and that is I want to give a shout out.
You had a joke in there though, right? Because you talked about it's a sign. What the heck does it have to do with a triangle?
True. I do want to give a shout out to all my folks in Boston Strong. A lot of people would have been cheering on marathon runners today, and it breaks my heart that that's not happening. But Boston will recover, and there'll be a marathon in the fall. That's what I'm hearing.
I believe we have a reader friend who was going to be participating actually this year.
Yes, I'm sure there's a lot of people watching us right now who would have been involved in that race. Okay, so go ahead and
all right, so first we have to, this is our review, right? What the heck's the mean value theorem? So
right.
Let's, if I can get this to work. Hey, okay. So the mean value theorem, this is the version in the CED. I think our key that you'll see in a couple days will be a little different. If a function f is continuous over the closed interval a to b, and differentiable over the open interval AB, then the mean value theorem guarantees a point within that open interval where the instantaneous rate of change equals the average rate of change over the interval. That's a lot of the word interval. So,
yeah, but English is like that. English is just too much, and math is so much tighter. And I see pretty much those words over on the side there, mathematically.
in fact, well, we were given the fact that this function is continuous and differentiable in that closed interval, so we're good for that.
That's important. Yeah.
In fact, I don't even know. Did it say it was differentiable, or did it say it was continuous, or did it only say differentiable? It said differentiable, but what does that mean?
Differentiability implies continuity, so we know, and then we need to state it as well.
We would have to state that on an FRQ. We have to make that connection because continuity is a requirement here, and we know continuity, but the reader doesn't know you know. And then it says there's a point within that open interval where the instantaneous rate of change, well, that's that g prime of c, right? Our function here is g, so that's our instantaneous rate of change, equals the average rate of change, which is the slope of that secant line from endpoint to endpoint. And you're seeing that as that blue line, and it lines up with the blue part of our equation. Think we're ready?
Well, I hope everyone has in their mind how many lines parallel to that blue line are tangent.
How many times is the, right? How many tangent
think
lines
about
are
it.
parallel?
How many tangent lines are parallel to that blue line?
And I'll be honest, when I did a very similar problem on a released exam, I used my pencil. I just set my pencil down and then just slid it down the page. Kind of like this.
One.
So there's one. Yes. I was telling Verge this morning, I kind of disappointed myself. I didn't put count font count there. But two. And lastly, a third time.
A third time.
So there they all are. So how many times does the theorem guarantee?
So this is called an existence theorem. So if the conditions are met, then there's at least one. That's how I like to think about it and say it. But Mark says the phrase a point guarantees a point encompasses that idea of at least one. And I'm happy to concede that to him.
I'm so glad you agree with me and the people who wrote the CD. Yeah, I think, the difference is guaranteeing a point means at least one versus guaranteeing exactly 1 point, which would be a stronger statement. Okay, so I hope everyone's good with that. You can see the green lines are that derivative right here, right? And then those are these guys, 1, 2, 3. And then the blue is our secant line that we're trying to be parallel to.
Yeah, and if you want to pause your video right now, in that shared folder, there is a template for the notes. And actually, there's a place where you can write all this stuff down for yourself, either now or later, because you definitely want to write these definitions down and things like that.
All right. So now I need to got to get my controls to hover correctly for me.
Yeah, we're playing with fire here because Mark's going to do something.
I'm in the same setup I was when I crashed a week and a half ago. So knock on wood. All right. I need to. Oh no. Sorry, I'm moving my chat box around that you guys can't see, but so I can read. All right, so this is number 2. We've actually talked about this problem, I believe, once before, or we at least included it in one of our very early lessons. But this is number 2 from the 2019 exam, I believe, from last spring's exam. It says the velocity of a particle p moving along the x-axis is given by the differentiable function v sub p, or velocity of p, where v sub p of t is measured in meters per hour and t is measured in hours. Selected values of v sub p of t are shown in the table above. Particle p is at the origin at time t equals 0. And you can see they have given us velocities at time 0, 0.3, 1 7/10, 2 8/10, and 4. It says justify why there must be at least one time t on the closed interval from 3/10 to 2 8/10 at which v sub p prime of t, the acceleration of particle p, equals 0 meters per hour. And this was a calculator active problem, but you will find that you do not need a calculator for this, I hope. Although you're free to use one if you're feeling a little unsafe. So what are some cues that this is relevant to what we were just doing? What do you think, Verge?
Well,
I'm seeing this at least
well,
one
that,
time.
okay, at least one time. And then we're seeing a derivative. So we're going to have to calculate a derivative or an approximation of a derivative. Yeah, and we've got this closed interval.
So it's kind of the left-hand side of that mean value theorem.
Mm-hmm.
And then we have these closed intervals, and I don't know how fancy I want to get with colors here. Like you said, playing with fire. So we're looking at the, whoa, oh well, live with it. We're living with these
good.
pairs. And so I'm going to do my y values on top, right? So we're going to do v of 2.8 minus v of 0.3.
By the way, your y values on top is a great reminder. We see so many students put the x values in the numerator, but we're calculating a slope here, change in y over change in x. Make sure your y values are in the numerator.
Y, rise over run, and if you go with a rhyming scheme, right? Y's over run from your x's. It's wise to run from your exes.
Oh, it's like wise to run from your exes. Oh my goodness. I'm hearing all sorts of new stuff in these last few weeks.
Not very useful stuff necessarily, but there it is. Okay. And I don't have to simplify the bottom. I really don't have to simplify the top. I do need a numeric answer. So those 55s have to be substituted in, but you know, that's 0, right? So
yeah.
Now, I've shown some work. Have I completely justified it yet?
No, you have not.
What are my conditions?
You need to really talk about continuity on the closed interval and differentiability on the open interval. And we weren't told that this function v sub p of t is continuous.
But we were told right there that it's differentiable.
Mm-hmm.
And thus continuous.
Yep.
So that connection has to be made. And did I leave a u out? Continue. Yep. All right. That's when I mumble with my handwriting. Okay. We've been told it's differentiable. We have to make that condition. And I know a lot of people are like, well, that's obvious. Everyone knows that. Well, you have to tell us that you're one of the everyone that know it. We only know what you write. So v of p is differentiable.
I hope there's a certain one of my students that's hearing what you're saying right now.
Are they related to you?
No. Oh, well, no, actually not.
I imagine he's actually very acute to that stuff. Okay, so since, how do I want to say it? I don't
since v sub p is
because of that, right?
I'm
gonna actually go back. Let's see. Do I have an eraser? The eraser did not work well in dress rehearsals. Okay, good. And then I'll come back to my pen. And I think I'm going to come in and do some green. Since that's true, there must be a C inside the open interval such that, and excuse my handwriting, but I'm writing on a tablet with a plastic pen, so you get what you get, such that v prime p of c equals 0. So it's things you have to do. You have to tick off your conditions, right?
Mm-hmm.
And we have 3 conditions. We've ticked those off, and then we can say our conclusion. Notice I didn't say by mean value theorem. Absolutely would be okay to say by mean value theorem, but unless you're asked to name the theorem, you don't have to name a theorem when you use it. Just have to satisfy the hypotheses and state the conclusion. How's that look, Verge? Is that gonna keep our counter going for another day?
I think it's fine. I mean, I think people might want to be a little bit more like nitpicky about making a statement of continuous on the closed interval and differentiable on the open interval, but we were told that this v sub p is differentiable everywhere. It's a differentiable function, so that implies continuous everywhere. So I don't need to appeal to an interval in this particular case, I don't think.
Okay. Yeah, I might even add the word everywhere under continuous, but.
Mm-hmm. Okay.
All right. So this is number 6, and this is where we ended Friday, I believe, correct?
It is, and we did not have D there as a question on Friday. We only had A, B, and C. We had, well, we, meaning Mark, had peeled the D off because he knows how to do that kind of stuff on a PDF. But here it is, and now we're ready to talk about D.
Now we've put it back and taken A, B, and C off. So,
yeah.
So just a reminder, we're being given this tabular information about G and G prime, a piecewise function of H, and the function F is this. I guess it's a sum of composite functions, cosine of 2x plus e to the sine x. Let G be a differentiable function. The table above gives value of G and its derivative G prime at selected values of x. And let H be the function whose graph consisting of 5 line segments is shown in the figure above. And there's a lot of information there we actually don't use in part D. Is there a number C in the closed interval -5 to -3 such that G prime of C equals -4? And justify your answer. This sounds very familiar.
Try to check if there's a.
Oh no!
What'd you do?
Sorry about that. It did not give me the pen. Okay, so I was trying to do this. These are values of x, right? So we're looking at this row in the table and this row in the table. How do we know we're looking for mean value theorem?
We're trying to figure out on that interval, is there a place where the tangent line slope is equal to -4? That's how I'm reading it.
Yeah, and it's not the C. Please don't be like, oh, if I see a C, it's mean value theorem. It could be G prime of K or lots of other stuff. But in this case, they happen to use the C, which is awful nice. But it's that instantaneous rate of change, which Vert said very nicely. I will tell you, when I first did this the first time, I came very close to writing something wrong. I started to grab off values of G prime. So I'm just.
Well, then your answer would have been no.
Exactly. So I just want to remind myself over here that this is G of B minus G of A, and wow, that's a sloppy notation there. We're worried about not having enough to do today, so that'll take some time. Oh, I did it again. Oh, I'm going to be so much better with this by the end of the 2 weeks. Okay.
Because this is not the first time he's doing it. I had to watch him do it for a long time.
And I usually do it with a Promethean board, which is a lot larger when you're standing in front of it. All right. So I reminding myself that it's instantaneous to average. And so I'm going to be pulling from this part of the table. Before we do that this time, let's go ahead and go, let's go ahead and get part of that since G is a differentiable function, G is continuous. On -5, -3. And then we're going to say also, and we're going to see how this works. I'm pretty sure it's going to work. We're about to say yes or no, so I can actually start this way regardless. So I'm going to do G of -3 minus G of -5. Order doesn't matter as long as you're consistent. If I did 10 minus 2 on the bottom, I would just have to do G of -5 minus G of -3 on top, right?
Yeah, but you need to fix your denominator.
Oh, but those are the values. Yes, they are. Thank you for catching that. I wouldn't want 10. I wouldn't want 10 minus 2 no matter what. So I went and pulled. So no.
You want you
Oh,
want
but I want the 2.
No. You want the x's in the denominator. -3 minus -5.
So silly.
Not
that silly that we need that. I'm being silly. Just
well,
these
sometimes
guys,
when
the
you're
B and A, right?
Yeah.
So then we get 2 minus 10 over -3 plus 5, which looks a lot like -4. So we can guarantee that G prime of C equals 4, -5, -3. And you'll notice it actually said in the closed interval, but if we can guarantee it inside the open, we're also guaranteeing it inside the closed. So.
And I would say that these two examples are really nice, lovely examples where you do your secant line slope, choosing the endpoints that are given, but there's been times where you actually want to look at actually an interior. Am I right about that, Mark? Where
yes, yeah, we're
much harder. We'll look at those like in a few days.
Yeah, I actually know of one case you're talking about where you actually had to pull different values off the table to get the slope you wanted.
Yeah.
But I believe the slope was something easier to spot, like just 2. So you just had to look for it to double over an interval or something like that.
So that is possible, and you know, anyway, just a little extra commentary there.
Just keep watching.
Yeah, just keep watching. Exactly.
Stay
All right,
tuned.
this is the notes page. So Mark is switching to his hover cam. This is exciting. And you can see there the top where you can hopefully have already filled in.
And Verge brought this, you know, I'm using Verge's technology here, but I pre-cut. so yeah, this is in the Dropbox. This is the warm up again.
That looks like you're selling a couch or something, like tear off here.
Have you seen this problem? So now, given that g of x is the same function, and so what Nicole I just got a message from a friend. Hold on.
So this is the same picture from the warm up, is what Mark was going to say, and we're going to give a whole lot more information.
I may need you to grab this from me.
Okay.
Okay, hold on, maybe not. I'm gonna have to stop share. It's not letting me stop my share. There was a mistake on the last one though. This is where I froze up last week. I have a little more control though now. This is interesting. Okay.
Just go ahead with that and we'll fix the mistake later.
Okay, g prime of c has to equal -4. I can't stop. Okay, there we go. Sorry about that.
You know what? You need to switch your background still too, Mark.
Well, I can't do that without a gray box coming up, so.
Oh, well, you guys have got to keep watching because it's Meme Monday and it's really, really good.
Okay, so let's see. I can't even get into my, this.
Oh,
it won't let me
I
write.
see it.
That g prime of c should be -4.
Yep, good. Thank you.
And for some reason, it won't let me draw on it anymore, and it's being all fussy, so.
Well, we'll take a screenshot of it and fix it for tomorrow.
Yeah. Oh, I bet I know the problem. What are you seeing right now, by the way?
I'm seeing all the green writing on that.
Okay, so you're still seeing what you should be seeing. It's not even letting me get in. Okay, let's go. Keep. There we go. That shouldn't. Okay. Sorry, folks. Hey, isn't it exciting when this happens, though? I'm going to try to bring this in one more time, and we're going to fix that. That's not even the right slide, is it? Can I write on that? It won't let me write on it.
But you can hover your cursor where you're talking about, maybe. I don't know. I can see it all the way down at the bottom there. On the bottom left, it should have said g prime of c equals -4 on that interval.
Yeah, for whatever reason, it's just not letting me edit it. Oh, well.
It's okay.
Wow. All right.
That does not count as a mistake because we want to fix it, and we.
Although technology-wise, this may count as a mistake. Okay. All right, let's just get to the camera. All right, I know how to work physical. All right, so yeah, so these little tear-offs is so I can work underneath them. So I pre-cut them. All right, so now we're giving you some more information because don't we all love to have more to do? It says, now given the same function shown above, it has x-intercepts on the interval -4 to 4 at x equals -3.8, -1, 0, and 3.4. Also, g of x has horizontal tangents at -2.9, -5/10, and 2 2/10. Finally, let h of x be a twice differentiable function such that h prime of x equals g of x. Okay. All that information. So this is now g of x, but it's also h prime. And they want us to give reasoning on what open intervals is h of x increasing. Well, when is h of x? The easiest test for that, and it is a test, not a definition, is we want to look at where is hx greater than 0? H prime of x. And so I happen to have a graph of h prime, and it looks like it is positive from -4 to that x-intercept, which is -3.8. And then again between -1 and 0. And then at that last x-intercept to 4. So 3.4 to 4. So it's those three intervals. And it asks specifically for open intervals here. We can talk more about that later if you guys want to email me or ask me, but they would be closed if we wanted to be in a textbook level of quality, but open is going to be fine for us and fine for the AP reading. But we were going from -4 to 3.8, -1 to 0, 3.4, and it said give a reasoning. And again, I'm going to make this connection that I'm actually looking at g equals h prime is greater than 0. And should I repeat them, or do you think I'm okay just to say on those intervals?
I think that's fine. Yeah. It didn't say justify, you know, I mean, when I wrote these notes up, I just said give reasoning for each, or give a reason for your answer.
Yeah.
Yeah. So there's that connection that you can make a conclusion about h because you're looking at h prime, and you know that h prime is the same as g, and you're looking for h prime to be positive, greater than 0. You could write h prime is positive, you know, you can write that out in English, but it's
Right.
quicker to write
Absolutely.
it out in math.
Right. And then they ask for the decreasing, and it's just going to be the complement sets, right? So from -3.8, you know, if we want to think of this too as, you know, this is my positive, my negative, my positive, my negative, my positive, and those are my
Physically,
slope
yeah.
values.
Yeah, h prime is above the x-axis, then below the x-axis, then above. And so that's what's happening on h prime. So it's giving us information about what would be happening on h.
So yeah, and we're just plotting individual tangent line slopes, right? And they're all being plotted in the negative quadrants. So -3.8 to -1, and then from 0 to 3.4. And this is because g equals h prime is less than 0. And again, just like Verge said, you could write that out in words.
But the connection between g and h prime is key.
And when we put the key up on Wednesday, on that one, I actually did repeat the intervals each time, and I put a conjunction and in there and things like that. So, all right, questions about 1 and 2? Things you want to add?
Looking good.
All right, take those away. Calgon. That is a reference that most
Nobody's
of you should
gonna
not get. Yes.
Yeah.
All right, number 3. On the open interval, -4 to 4, and again, this is a contextual thing, right? Like, how do you know that's not a point? Because it doesn't say at. What are the x coordinates of each local or relative maximum on h of x? And again,
Prepositions are so important in English.
and you have to be very careful, right? Because it'd be real easy. Oh, I see a local maximum right there. But it's of h, and this is h prime. So I want to look at places where the function exists, and it is, and we know the function exists everywhere because it's differentiable, so it's continuous. I also want to know where it goes from increasing to decreasing. And I measure that by looking where h prime changes from positive to negative. So I have positive to negative right here at that x-intercept, which is -3.8. And I'm going to actually put the word both here in front. And it looks like it goes positive to negative at the origin, or through x equals 0. And then at the other times it crosses, it's going negative to positive. So that's it. We're only looking at the open interval, so I don't have to worry about whether your textbook considers an endpoint one or not. Oh, someone just sent me a photo. Don't send me a photo while I'm talking. I'm sure it's a photo of my screen, but both x is -3. X equals 0 because G equals h prime of x changes from positive to negative at each.
Do we have to say that G equals h prime of x equals 0 at each of those spots as well?
It probably would be safe because it's continuous.
Mm-hmm.
So,
I mean, if we were justifying, we would absolutely have to say that.
So yeah, it's probably better with that.
Mm-hmm.
This is funny. I'm getting texts from my phone, but I don't know where my phone is. Okay. All right. So on to number 4. And if you even if you haven't seen this document, can you guess what number 4 is?
I can.
Yeah, you have inside information. Where are the minimums? Or the minima? And there's going to be 2 of those. And we want to look where h exists and is changing from negative to positive in its first derivative. So we know it's changing from decreasing to increasing and exists. So we're looking at x equals -1. And so that's right here where we switch from negative to positive. And over here, again, these values are given in our stem. That's why that was so important. And x equals 3.4. Because g equals h prime of x equals 0 at those locations. What are those called when they equal 0 there, Verge?
Critical numbers.
Yay. And critical numbers are the only places that relative min and max can occur in most textbooks.
You know, actually, aren't those like considered stationary points because they're like critical numbers have other kinds of numbers in them? Like
the only other things you can have are undefined derivatives, but the function has to still exist.
Yes. Yeah. Like if you had a cusp or something like that. I mean, that could be a location on the original function. Yeah. I don't know. I've heard that term stationary points. I don't usually use it, but anyway.
So, okay. The question, the picture was an emoji, which was a laugh at the 30-second delay into me reacting to the correction on the PowerPoint. All right. In any case, 3 and 4 were all right.
Yep.
Okay. I'm gonna slide that out and go to a new piece of paper.
So if you, I mean, this is a review, so you guys already know all this. So we've talked about increasing, decreasing, or maxes or mins or whatever, but there's something else you could talk about with functions, and it has to do with second derivative. So what might that be? What might Mark be putting up in a little strip next?
Sorry. I was going to try and change my background for you, but all right. So 5 and 6. Where are we concave up and where are we concave down? And I am just going to go ahead and look at, the reason, the give reasoning is the explanation for how we're getting our answer, right? So concave up is going to be, we test for it by looking at second derivative equal to or greater than 0. It's can be defined as where h prime is increasing or where the tangent line is below the curve. So I'm looking for where I'm increasing. I'm going to change colors here. We're going to start marking this thing up because I don't have to use it a whole lot more. Let's see, red's always nice. So from here to here, we're increasing. So that'd be h double prime positive. And then from here to here. I don't know why I put a parentheses on that one. All right. So that I need to go from peak to peak, and the peaks occur at these handy horizontal tangent locations that the author gave me. So between negative 2.9 and 0.5.
Negative 0.5.
Oh, thank you. Man, I am having issues with my negatives today.
It's okay.
And from 2.2 to 4. And that's because h prime is increasing on those intervals. I am going to avoid saying because the second derivative is positive, because if I say the second derivative is positive, I have to give reasoning for how I know that. And how do I know the second derivative is positive?
You'd have to talk about it a whole lot more probably than just making a statement of it.
I mean, my justification for H double prime being positive is because H prime is increasing. That's the information I've been given. You want to use what you've been given, and we've been given H prime. If I'd been given it in an algebraic sense, then I would just find the second derivative and use the second derivative. So where are we concave down? Well, where we're decreasing. So -4 to -2.9. See if I can get through all my negatives correctly. And -0.5 to +2.2. We'll use the backwards E ampersand. And again, I know this because this is where H prime is decreasing. Yay. We have one more type of question we can ask, right?
Yep, I think people can probably figure it out. If we've talked about concavity, we probably want to like leave no stone unturned to make sure
we talked about increasing, decreasing, followed by min and maxes. So now we talked about concavity and the inflection point or points.
So on this one, what are the x coordinates of each inflection point on h of x? So not needing to find a y coordinate, that might be subject of tomorrow.
Yes, absolutely. Yes. Need a little more information to find the actual point, but just the x coordinate. And we're looking for places where we change concavity. So I'm going to bring back these two guys.
And this is truly analysis. I mean, like you are analyzing this graph of G, which is H prime.
We have a change at -2.9, right? And we have a change at -5/10. And 2.2. Are there's three of them?
Yes, there's three because there's those three horizontal tangents.
Yeah, interesting. And my reasoning, because those are locations, and I actually, you know what, I'm gonna say those values. Of relative, I'm not gonna abbreviate. This I'll abbreviate. On my derivative, or on H prime. I want to say specifically which derivative. And that is actually a way to test for points of inflection. Relative max and min on H prime, when given H prime, is the most direct reasoning. I could also say because the concavity changes, but how do I know the concavity changes? Because I know the second derivative changes from positive to negative or vice versa. But then I have to back that up to the information I've been given. And so I would have to say because H double prime changes from increasing to decreasing, which I know because H prime changes from, H prime changes from increasing to decreasing. So it's easier just to, it's much easier just to tag out those relative max and mins on H prime, because the only way you're going to get a relative max or min on an interior point is you are changing from decreasing to increasing or vice versa. All right.
Okay, so I'm going to do my best to try and do a free response question with everyone right now. So let's see how that goes.
And I'm going to try and convert my laptop back to laptop mode, so hopefully I can get some more controls.
So this is in the shared folder. This is.
Are you sharing it? Okay.
Yeah, I'm sharing. Can you see it? Okay. Yep. I took the date off of it. I can't remember what date it is, but this is almost a mirror image and a little bit of a vertical translation from the graph we were just looking at. And we're told here on this problem, we are given the graph of f prime. And here's all the given information here, and then I'm going to read part A as well. The figure above shows the graph of f prime, the derivative of a twice differentiable function over the interval from -3 to 4, the closed interval. The graph of f prime has horizontal tangents at x equals -1, x equals 1, and x equals 3. So little horizontal tangents here. The areas of the region bounded by the x-axis in the graph of f prime on the intervals from -2 to 1 and 1 to 4 are 9 and 12 respectively. Now, like this is not going to be important at all for any of the unit 5 stuff, because that's going to be where we're really trying to figure out the value of the max or the min using a definite integral. And so we'll be working on that kind of stuff tomorrow. Whether we work on this exact problem is a different story, but we're not going to actually use that given information in the examples I'm going to do. In any case, part A, find all x coordinates at which f has a relative maximum. Give a reason for your answer. So where f has a relative maximum, I would want to look and see where does f prime equal 0, first of all. And I can see that f prime equals 0 at these 3 x-intercepts. Okay, I don't have to write them all down because only one of them is going to end up to be where the relative maximum occurs. By the way, you could say relative max or you could say local max. Is there anything else we could say besides those two terms, Mark?
Oh.
No? Okay.
I'm thinking, it's like,
oh, you're thinking?
Yeah. Those are the two most common for sure.
Okay. So f prime of x is equal to 0 at these 3 locations. Again, you don't really have to talk about the 1 and the 4 because they're not going to actually answer the question. We want the sign of f prime. We want f prime of x is actually greater than 0 for the interval. And I'm just going to go ahead and say from -3. Well, I'm going to say when x is less than 2. Sorry, -2. We can get into a lot of parentheses, brackets, arguments, and we're not going to. That's why I'm just going to be trying to be careful about this kind of stuff. So we know that f prime of x is greater than 0 when x is less than -2. And we know that f prime of x is less than 0 on the interval from, let's see, -2 to 1 with parentheses. Therefore, there's a relative max at x equals -2. I could have said f prime of x is positive, like write it out, in English. F prime of x is negative, write it out in English, be fine.
Right. And the of x's aren't necessary, but with the prime, it sometimes helps you see it, right?
True. Yes, absolutely. So those would be there's actually only one x coordinate, x equals -2, at which f has a relative maximum, and here's the reasoning for my answer. It doesn't really matter whether you answer the question first and give the reason after or vice versa. And I think Mark was kind of talking about that on those mean value theorem ones. You can kind of state the conditions at the end, or you know what I mean? Like it doesn't have to be perfect.
Even those notes ones, you have to reason through it, right? Before you can.
True, but with the amount of time that's afforded on the AP exam, we know that you don't have time to kind of clean up your proof like you might in a assignment situation, at home or whatever. So here's I'm selling my couch now. So here's part B on that same question. Let's see if I can get it to where I have enough clean space. Part B, it says, on what open intervals contained in -3 to 4 is the graph of f both concave down and decreasing? So concave down really means, like Mark said, as I think about this, I want to be thinking about the second derivative being negative. Decreasing, I want to think about the first derivative being negative, being less than 0. So as I look at this graph, the first derivative is less than 0 or equal to 0 pretty much the whole time, from -2 on, you know what I mean?
That thing is decreasing from -2 to 4.
Yeah. And then, so the question is, where is it also, so this is happening, when x is greater than -2, basically, that f prime is less than or equal to 0. In terms of the concave down, we're looking for f prime to be decreasing. Where is f prime decreasing? Well, f prime is decreasing here, like Mark drew on his. It's kind of off the screen. That's better. Right. And also here, okay, is where f prime is decreasing. So really, the intersection of these two intervals, x is greater than -2, And then also here from -3 to -1 and from 1 to 3, the intersection is going to be -2 to -1.
Yep.
And also 1 to 3. So that's going to be my
Yeah.
answer for B, -2 to -1 in union with 1 to 3. And you don't have to say in union with, but I tend to do that instead of putting a comma.
Yeah, we can talk later, but there's reasons why you don't want to put union for what it means in set notation. It's true on this problem, but it can actually be false.
Okay.
It's
well, that's good. I'm excited to talk about it later, and I'm ready to fight. No, just kidding.
Let's go. I'm already waiting for the email about that less than or equal to. I will tell you, I'm not going to answer those emails. You can go do your own research.
And we talk about it all the time at the AP reading, and we just we're talking about a Cal 1 level class, you know, and we're very with the rating of the question, so it's not as much of an issue. Okay, now here's part C. Part C says, find the x-coordinates of all points of inflection for the graph of f. Give a reason for your answer. Okay, so like before, the points of inflection are going to be the places where f prime is changing from increasing to decreasing, especially because like I'm looking at f prime. So I'm trying to think about how can I reason this with my given information. So it's going to be maybe some horizontal tangents, right?
Yeah.
So let's see here. I'm looking at probably happening at -1, also at +1, and then also at 3.
Yep.
Because here's my reasoning. F prime goes from increasing to decreasing, or from decreasing to increasing. So, and to be a little bit clearer, I might say, well, decreasing to increasing is happening at -1 and 3. I'm going to use that and sign again like you did. And then the other one going from increasing to decreasing is happening at 1, you know, at 1,
Yay.
something like that, at okay. So that's kind of a soft set of questions about this on the AP, you know, an AP free response. It's not really any sort of hard-nosed justifying. And so just a good one to kind of do today. Tomorrow, we're going to work on unit 6, and we're going to pull in ideas with definite integrals, which is going to make these problems a lot more challenging, I think. And also words like justify, which make them more challenging as well. Anything else on that, Mark, before you go ahead and talk about what's in the shared folder? Or I can talk about what's in the shared folder, either way. I'm not going to do part D on this one because it's a great one. I am going
to say, as soft as it was, because of all those give reasonings. I know this was I don't remember how this one did traditionally, but I know it took a long time to read.
Oh yeah, that I'm not saying it's no, I'm not saying it's easy for the readers to read it. I'm just saying like, yeah.
So, anyway, so what's in the Dropbox we'll go back.
So I think we've got the notes page, which includes those 2 warm-up.
All the things I was tearing off, yes.
And also the warm-up problems.
Hey, look, it says -4 now.
Yay! We can click up the clicker.
All right.
And we also have 2 circuits in there. They are not like, oh, exactly what we did today, but they are definitely topical. One's a mean value theorem circuit only, and then the other one is kind of more of a mixed bag, some related rates, some increasing, decreasing, that kind of thing.
It's kind of my base. It's for me, it's like unit 2 through unit 4. That's the one I wrote. It's I guess we're on 5 through unit 5 because there's mean value theorem on it. I do want to warn people about that one. It's a little different. There's a whole warning page when you open it, so you should be able to see this, but it says it's called a Mobius, not a circuit. And as Verge, if you've been here all along, Verge spent several lessons doing some Mobius and how there's a twist involved. So that it's just a pun on that. It's a circuit with a twist.
You don't have to cut your circuit into a Mobius
please don't.
strip.
If you've been doing our circuits all along, you've found that with a little backwards work, you don't have to do the last two because you kind of know where they have to go. And so this was my way of keeping my students honest. So when you finish, there will be either 2, 3, 4, or 5, if we bring those fingers back from the PowerPoint, left over. You'll feel like you finished early. You'll get done and there's 4 boxes left or 2 boxes left. Take any one of those boxes, call it A, and start lettering A, B, C, and so on. And when you close back up to A, that mini circuit will finish up and then every problem on the circuit is done. So there's a big loop and a little loop, and have fun with that.
Yeah, definitely. We are so appreciative of you guys watching us for each session. We have a lot of fun putting this stuff together for you, and we'll see you tomorrow. Unit 6 review. There's some good stuff in Unit 6.
Yeah, we're in the meat of the sandwich right now, aren't we?
Definitely. I'm hearing a U substitution and all sorts of good stuff.
Thanks for coming, everybody.
Bye.
Go that way, right? Exit that way.